this time. So we are talking about partial differentiation. Last day we went over all the cases of the chain rule. They're in the lecture notes. Let's do one more example and then we're going to talk about something else. So we're still talking about partial differentiation. Which example? Yeah, let's do this example. So if we have a multivariable function, t, a function of x and y, so maybe it stands for temperature. This will give you the temperature at some point x, y. And x and y themselves are functions of some other variables. X being r cos theta and y being r sine theta. Does that look familiar to you? Have you seen those expressions before? Okay, those are polar coordinates. We're going to talk about them again later, a little later in the course. Okay, but here we're interested in finding the partial derivative of t with respect to r. And we want to find the partial derivative of t with respect to theta. Why don't I write just a regular d, t d theta, or a regular d, t dr? It's because ultimately t is a function of two variables, r and theta. Right? If I take these expressions, r cos theta and r sine theta, and I substitute them everywhere I see an x and a y, then this function becomes a function of r and theta. So t is a function of two variables. So if I'm finding the derivative of t, it's a partial derivative. It's the partial derivative of t with respect to one, r, or the partial derivative of t with respect to the other, theta. Okay? Okay, well, we can use the chain rule if we're finding the partial derivative of t with respect to r. We can first find the partial derivative of t with respect to x, and then find the derivative of x with respect to r. Now, would I write regular dx dr, or would I write curly dx curly dr? Regular or curly? Regular fries or curly fries? When I'm finding the derivative of x with respect to r, is it a partial derivative or not? Well, we look at this function up here. Is x a function of one variable or more than one variable? More than one variable. So it's the partial derivative of x with respect to r. Okay, so if I'm finding the partial derivative of t with respect to r, I have to look at there's two places that contribute to that, x and y, because x and y are both functions of r. If I change r a little bit, that's going to change x and y a little bit. So I have to look at the partial derivatives of x and y. They both contribute to the partial derivative of t with respect to r. So I also have to add to that the partial derivative of t with respect to y and y with respect to r, right? The overall goal here is to find out how quickly does t change if I change r just a little bit. Well, there's changing r has two effects, x and y, so I need two parts to my partial derivative. And it's just the chain rule, right? And I said last day, don't be tempted to cancel these out. You can't do that because a curly x by itself does not exist. Okay, so you can't cancel these out and end up with partial derivative of t with respect to r plus partial derivative of t with respect to r is equal to partial derivative of t with respect to r. Mathematically, it doesn't make sense either. Okay, so you have to do these derivatives in the chain rule. Okay, so what's the partial derivative of t with respect to x? Well, we take the derivative with respect to x of our original t function, we hold y constant. So we get 3x squared minus y plus 0, because y is a constant when we take the derivative with respect to x. And now we multiply that by the partial derivative of x with respect to r. So we look at this function up here. Derivative of x with respect to r is simply cos theta. Plus partial derivative of t with respect to y. That's going to be negative x plus 3y squared times the partial derivative of y with respect to r is going to be sine theta. Now we were asked for the partial derivative of, there you're kind of done. I mean, you can multiply things out, but that doesn't do much. But we're asked for the partial derivative of t with respect to r. So that means our final expression probably should just have r's and thetas in it, not x's and y's. So we can now, wherever we have an x, we substitute r cos theta. Wherever we have a y, we substitute r sine theta. And over here as well. Okay, so now we're going to have an expression with just r's and thetas in it, no x's and y's. And again, we'd probably want to do that because we're looking for the partial derivative with respect to r. Okay? So when you do that and you simplify things a bit, you're going to get 3r squared cos cubed theta plus sine cubed theta minus 2r sine theta cos theta. Okay, so just some practice doing partial derivatives and using the chain rule. All right, any questions about that one? Okay, there's a couple more examples in the lecture notes that you can look at if you want some more practice. The last topic having to do with partial derivatives is linearization and what we call the total differential. Maybe you talked about the total differential in your math course last year. We'll just review it quickly in 2 dimensions because it's easier to draw, and then we'll expand it to 3 dimensions, which is what we're dealing with in this course. So if we're dealing with a 2-dimensional function that looks something like this, x, y is equal to a function of x. Now, at some point where x is equal to a, let's say x is currently equal to a, which means, we'll have y will be equal to the function at a, where x is equal to a. Now, let's say I change x by some amount. Let's call that dx. To this point here. Okay, so here the x value is a plus dx. Well, I can just put that new x value into my function, and I would get f at a plus dx, right? X is equal to a plus dx. So I can say, okay, if I change x by dx, in order to see how much my function changes, I just calculate the function value at a value of a, at an x value of a, and I calculate the function value at an x value of a plus dx. And the difference between these two numbers is how much my function changes, obviously, right? Okay, well, often we're more interested in how much is the function changing right at this point versus at this point, or some other point along here, right? And that's when we make dx really, really, really small. Okay, we can do the same thing. We can say, okay, I can find for an x value equal to a, I can find what the function value is, and then for an x value of a plus dx, where dx is really small, well, maybe that's right here. A plus dx is right here. I can find my function value at that value. I take the difference and I see how much my function changes. Or I can approximate this, okay? And we can approximate it with a derivative. We can say, if I draw a line tangent to the curve right at that point, and I find the slope of this line, how do I find the slope of that line? I can take the derivative of my function, right? The derivative of that function gives me the slope. I put an x value of a in there in the derivative of f, and I've got the slope of the tangent line at a value of x equal to a. If I put a different value of x, a plus dx, into this derivative, I get the slope of this tangent line. Okay, but I'm interested in this point here. So, okay, great. What does this give us? Well, again, we're interested in figuring out about how much does my function change if I change x by some value. Okay, well, one way to do it is to actually figure out what the function values are for these two different values of x and take the difference. Or we can approximate that. If the amount I change my x value is really small, I can really approximate how much my function changes by just looking at the slope of this line, right? Because if I find that, right? If I find this line, this tangent line, the slope of it is the derivative of this function at this point, well, this is just a straight line. And so I could say, okay, this straight line at an x value of a, I still have this value of y. At an x value of a plus dx, according to this straight line, I have this value for my function. Okay, it's a little bit different than the true value. But if I make dx really small, if I make dx like this, well, then the difference between the y value for the derivative and the y value for the actual function is going to get really close. That difference becomes really small. And my approximation of using the derivative to find how much my function changes for some change in x becomes very good. Okay? So sometimes there's certain situations, well, why would you ever want to do this? Well, in some situations, you might not know what the function for the curve itself is. You might not know this function, but for some reason you know its derivative. Well, if you know its derivative, you can use that derivative to estimate a change in the function for a change in one of the variables. Okay? And so in terms of total differential, well, what is the total differential? The total differential is this distance. Again, if my dx is this big, so forget about this red and blue line here. If my dx is this big, the total differential is the change in linearization. That's df. Regular df, because f is just a function of one variable x. Okay? And what is df equal to? df is equal to the slope of that tangent line, which is the derivative calculated at an x value of a, times how much x changes, dx. Okay, that's our total differential. So if I want to approximate how much the function actually changes as x changes by amount dx, I can approximate that using the total differential. This is an approximation. Really, the true change in the function is this distance here. True change in function. I have to have the function itself to figure out what that is. I got to put the value x is equal to a into that function, I get a value for y. I put a value x, a is equal to a plus dx into the function, I get another value for y, another function value, I take the difference, I got the true change in the function as x changes by dx. Or I can approximate it using this total differential. It's an approximation, but it's a really good approximation if dx gets really small, right? Because if dx gets really small, then I'm just looking at, the tangent line and the function are almost exactly the same. So the derivative becomes a very, very good approximation for what happens in the function. Of course, if dx is really big, well, then I start getting this difference, right? Depending on what the function does. Okay, so that's total differential. In 2 dimensions. In 3 dimensions, we're not dealing with a curve in 2 dimensions, but if I'm dealing with some sort of If I'm dealing with some sort of function now, z is equal to some function of xy. So I've got a multivariable function. What is that? That is a surface in three-dimensional space, right? So now I could say the same thing. How much does z change if I change x and y a little bit? Okay, that's what I'm interested in. Up here in 2 dimensions, I was interested in how much does y change if I change x a little bit? Well, now I've got a function of 2 variables, so I'm interested in how much does z change if x and y change a little bit? Okay, that's what we're interested in. Well, one way you can do it is, obviously, if you have this function, you can plug in the initial values for x and y, get a value for z. Then you can plug in the new values for x and y. X and y have changed a little bit. Get a new value for z, take the difference between those two z values, and you got how much z has changed. Or you can approximate it using a derivative. Okay, and that's what we're going to do. We have the same thing, so let's just write it out here. If moving from point x naught, y naught to a nearby point, x naught plus dx, comma, y naught plus dy, I forgot the dx. Okay, so the resulting change in the linearization of f. When we're dealing with the derivative, we're dealing with a line, the slope of a line in 1 dimensions, or the slope of a plane in 3 dimensions. In 2 dimensions, we're dealing with the slope of a line, if we're talking about a derivative. In 3 dimensions, we're dealing with the slope of a plane, right? And it would be the plane tangent to this surface defined by z is equal to f of xy, okay? At the particular point where we're finding this point x naught, y naught, that's a point on the surface, right? Or it corresponds to a point on the surface. We can find the plane tangent to that surface at that point, and we can see how much x changes and how much y changes. We can find the partial derivatives. Remember, f sub x is a partial derivative. So we find the partial derivative of this function f if we change x by dx, and we can find the partial derivative of this function in the y direction at that point times dy, right? It's the same thing as up here. The total differential in two dimensions is equal to the slope of the function at that point times dx, how much we changed x. Here we've got 2 variables because we're in 3 dimensions. So again, this is a derivative. It's a partial derivative in the x direction. So it tells us the slope of the function at the point x naught, y naught if we move a little bit in the x direction. So you take that slope and you multiply by dx, and that's the contribution of a change of x to the change in my function. And you add that to the slope of the tangent plane to the function at the point x naught, y naught in the y direction, multiplied by a little change in the y direction. Okay? So it's exactly the same form as this, but we've got 2 terms now, because we can take the derivative in 2 directions, x and y. Okay, so that's our total. This is our total differential, and it is a change in the linearization of f, right? F is presumably a nonlinear curve, just like up here. This function here is nonlinear. It's not a line, okay? And when we're dealing with nonlinear functions, sometimes they're a royal pain in the rear end, right? They make the math difficult, and so often what we do is we approximate them with a linearization, right? Again, in the region of this point here, This straight line pretty much looks like the function. Yeah, you know, if you look over the whole function, the line doesn't look like it, but just over this small part of the function, a straight line is a pretty good approximation of that function. So often when we're dealing with nonlinear functions, and whatever we're doing, we actually linearize the function by approximating it with a straight line. And straight lines are easy to deal with, okay? In my field of research in GPS, we have to do this linearization, the equations that you have to solve to figure out where your GPS receiver is based on signals that you're receiving from GPS satellites is highly nonlinear, all right? In order to make the math a whole lot easier, we linearize those equations. Now it's an approximation though. As soon as you linearize a nonlinear function, you're doing an approximation. But if the conditions are right, the approximation is often very good. Okay? Okay, so again, this total differential is not the true change in the function. It's really an approximation in the change of the function as you go from this point, x naught, y naught, to a different point, x naught plus dx, y naught plus dy. Okay, so let's look at an example of this. Well, before we do that, let's also write this down. If we're dealing with a fourth dimension, so if we got 4 variables in our equation, or we have a function of 3 variables, well now the total differential of f, or the total differential of w, whatever you want to call it, is going to be the partial derivative of our function with respect to x dx. Partial derivative of the function with respect to y dy, partial derivative of the function with respect to z dz. Okay, so you change x, y, and z a little bit, and you can find the total change in the linearization, which is an approximation to the total change in the function. Okay, so really what we should write then is how much our actual function changes is an approximation, so we don't use the equal signs, we say approximately equal to the value of the partial derivative with respect to x times some change in x plus the partial derivative of y times some change in y plus the partial derivative with respect to z times some change in z. Okay, so this is the approximation formula. Right? This part here is equal to df, and df is an approximation of the actual true change in the function. Okay, so let's look at an example, because that's all that really matters. Okay, so the question is, if we've got a cone, and if the radius of this cone is changed from 10 centimeters to 10.1 centimeters, so it changes by 0.1 centimeters, and the height of the cone is changed from 1 meter to 0.99 meters, use total differential to approximate delta V, the change in volume of the cone. Now obviously, if you had no idea what a total differential is, you could still calculate the change in the volume of the cone, right? Just calculate the volume of the cone with a radius of 10 centimeters and a height of 1 meter. You'll get a volume. Then find the volume of a cone with a radius of 10.1 centimeters and a height of 0.99 meters. You'll get a different volume. Okay, now you know how much the volume changed, right? You can always do that. But if you're asked to use total differential, well then you're going to approximate this change. not by calculating function values, but by using the partial derivatives, okay? So, well, first we need to know the volume of a cone, and you probably don't have that formula on the tip of your brain, but that's what it would be. The volume of a cone is 1/3 pi r squared h, so r is the radius, h is the height. So we've got a function of two variables. The volume is a function of radius and height. Okay, well, we're going to use this total differential here to approximate the true change in the volume. Okay, so we need the partial derivative of the volume with respect to r and with respect to h, and we need the changes delta r and delta h. So let's find delta r and delta h. Well, delta r is a positive change of 0.1 centimeters, right? We're also going to have to calculate the partial derivatives at some value of r and h. Okay, that corresponds, if I can go up here for a second, that corresponds to the value of x here if we're calculating the partial derivative, or the derivative of our function here, right? We have to find f prime at a, right? We need some value for x here. Same thing down here, we're going to need a value for r and h to put into the partial derivatives. Well, you typically will use the starting value for r and the starting value for h, okay? So delta r is going to be positive 0.1 centimeters, and r equals 10 centimeters. We're going to use r equal to 10 centimeters, not to where it goes to 10.1. We're going to use r where it started, at 10. Okay, delta h, how does the height change? Well, the height gets smaller, so that's a negative. And it gets smaller by how much? It gets smaller by also 1 centimeter, right? It goes from 1 meter, or 100 centimeters, to 99 centimeters. So it goes down by a centimeter. So it's a negative change in r. H, pardon me. And h starts at what? Well, it starts at 100 centimeters. So that's what we're going to use. We're going to use those, an r of 10 centimeters and an h of 100 centimeters for r and h values in the partial derivatives. Okay? Okay, now we need, we're going to use the total differential, which is dv, okay, which is equal to the partial derivative of our volume function with respect to r, dr, plus the partial derivative of our volume function with respect to h, dh, is equal to what? Okay, if I take the partial derivative of v with respect to r, that's going to be 2/3 pi rh. Multiplied by dr. Plus the partial derivative of v with respect to h. That's going to be 1/3 pi r squared times dh. Okay, well now we stick in our, pardon me. Now we put in our numbers. Okay, r, we're finding the slope of this function at an r value of 10 centimeters and an h value of 100 centimeters. And then we change r to 10.1 and we change h to 99 centimeters. Make sure you got your units straight, right? We were given some mixed units here, r in centimeters and h in meters. Either change them all to meters or change them all to centimeters, whatever, doesn't matter. But make sure you're not mixing units up. Okay, what is dr? Well, that's how much r changes, okay? That's our delta r up here, which is 0.1 centimeters. Plus 1/3 pi r squared. R, again, is still 10 centimeters. That's where r starts. Times dh, well, that's our delta h of -1. Okay, so this is the slope of our function in the r direction. You multiply that slope at an r value of 10 and an h value of 100 times how much you change in the r direction. That gives you how much does v change due to a change in r. And then you add to that the slope of the function in the h direction at the point r equal to 10 and h equal to 100 times how much you change in the h direction. Right? These two added up give you the total change in v. This part due to the change in r, this part due to the change in h. Right? And now you just crank the numbers and you will find you get 100 pi over 3 centimeters cubed. Okay? That is an approximation to the change in volume due to a change in r of positive 0.1 centimeters and a change in h of -1 centimeters. Another place that you'll see this is in what we call sensitivity analysis. Often we have a function which represents some physical quantity or phenomena, and we're very curious. We want to know how sensitive is that function to a change in one of the variables. Okay, that's used all the time in engineering. And so that's where you would use a partial derivative, right? How sensitive is my volume to a change in r? That's what this term gives you. How sensitive is my volume to a change in h? That's what this term gives you. How sensitive is the volume to a change in r and h is what the sum gives you, okay? So we're interested in this. This is, actually it's this partial derivative itself which tells you the sensitivity. If this partial derivative is equal to 0, what does that tell us about a change in v due to a change in r? If this partial derivative is 0, is the volume sensitive to a change in r? No. I can make dr as big as I want. If this partial derivative is 0, the volume doesn't change, right? So if the partial derivative is really small or 0, that means my function v is not sensitive to a change in r. That may be good, that may not be good. Depends on the application, okay? If this partial derivative is really, really big, that means I just change r a little bit and the volume changes like crazy. That means my volume is really sensitive to a change in r. Again, that might be good, that might not be good. Depends on the application. Okay, so you'll see that somewhere, I'm sure you'll see that somewhere along the line in your career here, sensitivity. Okay, sensitivity analysis just means let's look at these partial derivatives and see how big they are. If they're big, very sensitive. If they're small, not sensitive. Okay. There's another example. We won't take the time. You can look at it. It's just find the total differential of some function, and it's just finding partial derivatives again. So there's lots of examples in the lecture notes which are on Canvas that you can look at for practice. Okay, and of course there's questions like this in the assignments too. Okay, any questions about this? Okay, let's move on then. Next topic is what we call the gradient vector. Now that we know what partial derivatives are, we're going to kind of put them together into what we call a gradient vector. Okay, and I think I'm going to cut to the chase, and I'm just going to tell you what it is. If I've got w is equal to a function of x, y, and z, I can define what's called the gradient vector. And we use an upside-down triangle to symbolize it. We call it the del or the grad operator. So if I want to find the gradient of this function f, I'm actually getting a vector. And the components of this vector are just the partial derivatives of my function with respect to x, y, and z. That's all it is. Or, again, we could write it like this, using the, again, I should do this once in a while, in case you see this on a quiz or a final exam, using ijk for the components of our vector. Okay, that's what we call the gradient vector. It's a vector, and the components of this vector are the partial derivatives of our function. So really, it is a derivative. It's just a derivative in vector form. We found the individual components. We know how to find those now. They're partial derivatives. We put them together into a vector, and we got the gradient vector. Okay? Really, it's just the derivative of a multivariable function. If I have z is equal to a function of xy, my gradient vector will be a two-dimensional vector, with the first component being the partial derivative with respect to x and the second being the partial derivative with respect to y. If I have a function of x, y, and z like here, well then I get a three-dimensional gradient vector because there's three partial derivatives with respect to x, y, and z. Okay, so if I have some function of x, y, and z, and you know here maybe w, if you need a practical application, maybe w here refers to pressure. So maybe this function f tells me the pressure in three-dimensional space at a point x, y, z. Okay? So now I've got this, I can say, well, at each point, x, y, z, what does the gradient vector tell me? Well, it gives a vector at that point. It basically tells me what the derivative is of that function at that particular point in space. I can find the gradient vector at some other point, x, y, z. It'll give me another vector at that point in three-dimensional space, which tells me the derivative of the function at that point in space. Okay? So again, this is what we call the del, we often call this the del operator, because I think that symbol is called del operator, or we call it the gradient operator or the grad operator. All means the same thing. Upside down triangle. And all you do to get the gradient vector of a function is take its partial derivatives and put it into a vector. That's all there is to it. Okay? So you already know how to do the partial derivatives. Now you just put them into a function and you got the gradient vector. Okay, so we've been slowly expanding your horizon in terms of calculus. Last year you just dealt with stuff like that, right? This year we introduced you to the partial derivative, and now we're going to even compactualize that more, and now we've got the gradient operator giving us the gradient vector, which is really just a derivative. Okay? And the del operator by itself is an operator, right? So we can say that it is actually equal to the partial derivative of some function with respect to x with some function with respect to y, some function with respect to z, right? That's what del by itself is. You apply it to some function f, and it's the partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z. Right, I mentioned the Big Bang Theory television show. If you go back and look at some past episodes, you know how they always have whiteboards in their apartment and in their offices and stuff. I've seen the del operator on there. Now you'll know what it is, okay? All right, so that's what we call the gradient vector. It is a linear operator, so that means if we want to take the gradient of some scalar times one function plus a different scalar times a second function, well, that would just be equal to this, just like we would expect. And in terms of approximating the change of some multivariable function using the total differential, well, now we can have more compact notation by using the gradient vector, right? If we're going from if we've got a function of if we've got a function of x and y, and we're going from one point, x0, y0, to another point, xy, and we want to see how much our function changes, approximating that with the total differential. Well, we said that delta f, the change in our function, is approximately equal to, how do I want to write this? Partial derivative of f with respect to x times delta x plus the partial derivative of f with respect to y times delta y, right? That is our approximation formula. Well, this partial derivative and this partial derivative are just the x and y components of my gradient vector of f, right? So this is really just that, the dot product of my gradient vector, because in this case the gradient vector is equal to this vector. So the dot product of that with a vector delta x, delta y gives me my change in f, right? So again, you're multiplying a derivative by some change to figure out what the change in the function is. Okay, this vector is your change vector. It points from where the original value of x, y, x naught, y naught, to the new value of x and y, whatever it is, okay? So now, this though, it's the exact same thing as what we just looked at a few minutes ago. We can just write it differently now using the shorthand notation for the gradient vector. Okay, let's look at a couple of examples, and we're almost done. We got w is equal to a function of x, y, z, which is equal to x squared plus y squared minus 2z squared plus z ln x. We want to find the gradient vector of f, and we want to find it in general, and we want to find it at a specific point, x equal to 1, y equal to 1, z equal to 1. Okay, well, the gradient of f is just going to be equal to these three partial derivatives put into a vector. So we take the partial derivative of the function with respect to x. That is going to be 2x plus z over x. Right? Partial derivative of this here with respect to x is 2x. This is a constant, this is a constant, this is a constant times ln of x. Derivative of ln of x is 1 over x times z. So we get that. Okay, so that's our f of x. F of y is going to be 2y, and that's it, right? And f of z is going to be minus 4z plus ln of x. So there's my gradient vector, okay? So really what the gradient vector gives you is what we call a vector field. I can put any point in three-dimensional space, x, y, z, into there and get a vector, the gradient vector, at that point. I put a different value of x, y, z in, I get the gradient vector at that point. So I get a field of gradient vectors, one gradient vector at every point. All right, and we'll talk about that more next day. See you Friday.